You are falling in absolute darkness. Behind you, the universe shrinks into a single, violently distorted point of light. You have just crossed the event horizon of a black hole. Hidden across the universe are regions where reality itself begins to fail. They are not cosmic vacuums, but regions of space-time where gravity is so extreme that the fundamental rules of reality are completely rewritten. To understand why escape is impossible, we must abandon our everyday intuition and look strictly at the geometry of space and time. Because once you cross that invisible boundary, moving outward ceases to be a physical possibility. But if crossing the event horizon mathematically deletes every path leading back to the universe, where exactly does it force you to go? The mathematical boundary. To an outside observer, the event horizon looks like a sphere of perfect nothingness. It is not a physical surface. You cannot touch it, and you cannot crash into it. It is a mathematical boundary. It is the exact radius where the escape velocity required to leave the gravitational pull of the mass surpasses 299,792 kilometers per second, which is the speed of light. Because the speed of light is the absolute speed limit of the universe, nothing can escape. Saying gravity pulls you in is a vast oversimplification. It implies that a black hole is simply a very strong magnet. It suggests that if you possessed a powerful enough rocket engine, you could eventually thrust your way back out to the stars. This is mathematically false. You cannot thrust your way out. It is not because your engine lacks power. It is because the physical path leading out no longer exists in your universe. The tipping of the light cone. To understand why escape is impossible, physicists use a concept called the light cone. In everyday space, your future can take place in any spatial direction you choose. You can move up, down, left, or right. But massive objects warp space-time. As you get closer to a black hole, space itself begins to stretch and curve inward. This gravity does not just pull on your mass, it literally tilts your light cone toward the black hole. At the exact boundary of the event horizon, a critical geometric shift occurs. Your light cone tips over completely. All possible paths forward in time now point inward in space. Inside the event horizon, space and time undergo a literal mathematical role, reversal. In the outside universe, you are forced to move forward in time, but you can choose your direction in space. Inside the black hole, you are forced to move inward in space, just as relentlessly as you are forced to move forward in time on Earth. The singularity is no longer merely a place in space. Inside the event horizon, reaching it becomes as unavoidable as reaching tomorrow. Just as you cannot travel back to yesterday, you cannot travel away from the singularity. If you turn your ship around and fire your engines at maximum thrust, you will not move outward. No amount of acceleration can redirect your future away from the singularity. Every direction is down. Every choice is the singularity. Inside a black hole, escape is not prevented by force. Escape is removed from reality itself, the dragging of space. The scenario becomes even more complex when we account for rotating black holes. As a massive black hole spins, it literally pulls the fabric of space-time around with it. Around a spinning black hole, there is a region just outside the event horizon called the ergosphere. Inside the ergosphere, standing still becomes physically impossible. To remain stationary relative to the distant stars, you would have to travel faster than light. You are forced to orbit the black hole, swept up in a cosmic whirlpool of space-time, long before you even touch the event horizon. The outside observer. The extreme physics of a black hole create two entirely different versions of reality. Imagine an observer parked in a spacecraft at a safe distance, watching you fall toward the event horizon. According to general relativity, massive gravitational fields cause time dilation. Gravity slows down the passage of time relative to an observer in a weaker gravitational field. As you approach the boundary, the observer would see your movements begin to slow down. The closer you get to the horizon, the slower your clock ticks relative to theirs, but they do not see you cross the boundary. Because light struggles to climb out of the extreme gravitational well, the photons reflecting off your ship lose energy. Their wavelength stretches. Your image shifts through the visible spectrum, turning orange, and then a deep crimson red. This is known as infinite gravitational redshift. Eventually, the light stretches into undetectable frequencies. To the outside observer, you never actually cross the event horizon. Your image simply freezes, stretches, and fades. Your information is trapped in a frozen moment of time for the rest of the universe's existence. The reality of the fall. But the truly terrifying part is this. From your perspective, nothing feels wrong. General relativity dictates that your own clock always ticks normally to you. You fall through the event horizon without feeling a bump, a barrier, or any sudden transition. There is no warning, no wall, no visible boundary separating safety from doom. A common misconception is that you would see the end of time play out in fast forward. This is scientifically inaccurate. Because you are falling inward at near light speed, the light from the outside universe falls in with you and undergoes severe blue shift. The waves compress and gain immense energy. The universe behind you collapses into a blindingly bright, intensely radioactive halo of X-rays and gamma radiation. And then comes the physical toll of extreme gravity, the mechanics of spaghettification. Whether you survive crossing the event horizon depends entirely on the mass of the black hole. If you fell into a stellar mass black hole, you would be dead long before you reached the horizon. Gravity is a localized force. The closer an object is to a center of mass, the stronger the pull. If you fall feet first, the gravitational pull on your feet is exponentially stronger than the pull on your head. This difference creates tidal forces. In a stellar mass black hole, you are subjected to a process scientifically termed spaghettification. The structural integrity of your suit, your bones, and your muscles is overcome by the gravitational differential. You are stretched vertically and compressed horizontally. The tidal forces rapidly intensify as you fall deeper. Your cellular bonds fail. Molecular bonds shatter. Finally, atomic forces are overcome. Your matter would eventually be compressed beyond the point where modern physics can reliably describe what happens next, the breakdown of physics. All paths lead to the singularity. But what exactly is it? Strictly speaking, the singularity is where the equations of general relativity break down. When physicists calculate the density of matter and the curvature of space-time at the exact center of a black hole, the mathematics output infinities. Infinite density, zero volume. Infinite space-time curvature. In physics, an infinity in an equation means the theory is incomplete. To understand the singularity, we need a theory of quantum gravity to perfectly unite Einstein's theory of the very large with quantum mechanics, the theory of the very small. We do not yet possess this theory. Whether it is a single point of matter or a spinning one-dimensional ring, it marks the boundary of human knowledge. It is a region where our current understanding of physics ceases to function. The information paradox. For decades, scientists believed anything falling into a black hole was permanently trapped. But in 1974, physicist Stephen Hawking applied quantum field theory to the edge of the event horizon. Space is never truly empty. At the quantum level, virtual particles and antiparticles constantly pop into existence and annihilate each other. If a pair appears exactly on the boundary, extreme tidal forces can separate them before annihilation. One particle falls into the black hole. The other is propelled outward into space. To the outside universe, it appears as though the black hole is emitting a particle. This is Hawking radiation. Because the emitted particle carries energy, the black hole slowly loses mass. Over trillions of years, a black hole will evaporate. It will shrink to a microscopic size and violently explode, leaving nothing behind. This creates the black hole information paradox. A fundamental quantum law states information cannot be destroyed. The physical state of a system must always be traceable back to its past. But when matter falls into a black hole, its information is seemingly locked inside. If the black hole evaporates into featureless thermal radiation and ceases to exist, where did the information go? If information can be permanently deleted from the universe, then the rules of quantum mechanics are flawed. If the rules of quantum mechanics are flawed, then our foundational understanding of the universe is broken. Modern theories suggest the information may survive in ways we still do not fully understand. But no universally accepted solution exists: the limit of knowledge. Black holes are natural laboratories where thermodynamics, quantum mechanics, and relativity are pushed to their absolute limits. We expect the universe to be a rational, calculable place where equations hold true, mass behaves predictably, and time marches forward in a straight line. But black holes force us to confront that our understanding of reality is strictly localized. The rules that govern our solar system simply do not apply in the extreme depths of space-time. No triumph of engineering can bypass the geometric collapse of space-time. When an object crosses that boundary, it is subjected to the absolute mathematics of general relativity. You lose more than your location. You are removed from the causal structure of the universe. The cosmos will continue to expand, galaxies will merge, and the universe will age over trillions of years. But you will not be a part of it. You will have fallen out of time and into the absolute unknown.